Okay, thanks very much.
Mass and energy.
Okay, thanks very much.
20 minutes. 20 minutes.
Okay, sounds good. So the question I want to take up in this talk is how we should understand the relationship between energy and mass and special relativity. And I'll start by just surveying what I take to be the sort of canonical presentation of this relationship in most standard textbooks. And this won't, I think, be a surprise to anyone. There are two statements I want to read about this relationship to help sort of set the stage. One is from a textbook from the 70s. E equals mc squared is a statement that mass and energy are two forms of the same thing, and that one can be converted into the other. And the second one is from a general relativity textbook from the 90s. Ray Dinverno writes E equals mc squared is one of the most famous equations in physics. However, is not just a mathematical relationship between two different quantities, namely energy and mass, but rather states that energy and mass are equivalent concepts. So the question I want to think about is what these passages mean. Right? And in particular, this is how a traditional textbook develops the meaning of those sorts of passages. We start with the expression for the relativistic free energy of a particle. We do a Taylor expansion, and we observe that part of that Taylor expansion is a piece that doesn't depend on the velocity at all. That gets defined to be the rest energy. And then the other part gets labeled the kinetic energy, the free energy, the relativistic free energy of the particle due to the motion. It looks like we have just carved up this Taylor expansion, but I should just note in passing that you can get this expression for the kinetic energy just by doing the integral for the work using the relativistic force. So there's an independent motivation for thinking of this expression as giving you the kinetic energy. And then we get the claim that the rest mass, which I'm just going to call mass, and the rest energy are different ways of referring to one and the same physical property. Right? That there is sort of one property which sometimes gets called mass and sometimes gets called rest energy. And that seems to be the basic picture behind how most physics textbooks talk about the relationship between energy and mass. Good. So, one question we might think about is why this sort of expression, E equals mc squared, might tempt one to identify mass with a particular form of energy. Right? What is it about that equation that makes us think that they are in fact the same thing, rather than just two variables related by an equation? For, we don't identify photon energy and frequency, even though they are also related in fixed proportion. Right? So what is it about the E equals mc squared equation that's different, right? That leads people to identify those concepts. So I think there are two motivations that are typically given in textbooks. One concerns so-called mass defects associated with decay results. Right? So for example, the tritium nucleus decays into a helium nucleus, an electron and an antineutrino, but there's a mass defect. Namely, the mass of the tritium molecule is greater than the sum of the mass of the daughter bodies after it decays. So it looks like there has been some sort of conversion from mass or mass energy into, say, the kinetic energies of the daughter bodies. So one might put this by saying that the mass energy conversion occurs in virtue of the exchange of rest energy with other forms of energy. Right? So mass just gets identified with a particular form of energy which can be converted into other forms of energy. Right? And that's how the story tends to go. Another sort of motivation that's given concerns, for example, mass gains in inelastic collisions. So if we consider just a system of two equally massive bodies approaching each other in some frame where they have equal velocities, and then they stick together, right? It's just a very simple calculation to show that the mass of the single body afterwards is going to be greater than the sum of the rest masses before. Right? So here, the mass of the system is just the sum of these rest masses. This is the energy. Energy gets conserved, but now we're dealing with a single mass, so it just drops out of this sort of equation that the mass afterwards is greater than the masses before. Right? So these are the sorts of examples that one sees often to motivate why we should think about the equation E equals mc squared in a way different from the equation for the energy of a photon, for example. Okay, good. So that's the setup. What I really want to talk about today is a particular challenge that Mark Lang has raised to this sort of picture, and how I think one might try to the puzzles that his challenge raises and how I think we might try to get out of them. So in a paper, a 2001 paper and in a chapter from a 2002 book, he presents a puzzle about this identification, right, of mass as a form of energy. And the puzzle is fairly straightforward to lay out. We start with the observation that any property that isn't Lorentz invariant isn't physically real or objective. So what he means by that is something along the following lines. Only what is the same in every inertial frame is a genuine feature of reality. The value that any frame-dependent quantity assumes in a given inertial frame reflects not just reality, but also that reference frame's own particular perspective. The Lorentz invariant quantities are exactly those which depend only on how the universe really is, uncontaminated by any contribution from us in describing the universe. But then the problem is that mass is Lorentz invariant, but energy is not. And so, he puts it this way: consider a body's mass m. This quantity is Lorentz invariant and hence objectively real, but the body's energy is not, since its energy depends on its speed, and its speed v is plainly frame dependent. Right? And then the same issue arose in the context of classical physics. So we have this puzzle, right? Mass can't be a form of energy. Mass is an objectively real property according to this very widely accepted interpretive criterion for what sorts of properties are physically real, but energy is not, right? So what's going on in in the picture that is presented in most physics textbooks, and what's going on in those particular cases, right? Where it looks like there are motivations for thinking that mass is being converted into energy or vice versa. So this is the challenge. Now just one thing I should just say at the beginning to get out of the way is you might sort of wonder about this sort of argument, because you might say, well look, rest energy is Lorentz invariant, right? Even if total energy is not, right? And so can't rest mass still be identified with rest energy? But the challenge here, I think, is that it's very difficult to mesh that interpretation with the structure of the dynamics. In particular, it's one of the defining features of energy that can be converted into other forms of energy. So if rest energy were an objective physical property, but kinetic energy not, how could one be converted into the other? So you're still going to be left with this problem of a seeming conversion between an objectively real property that's Lorentz invariant and one that's not. Okay, so this is just a very quick slide. I'm not going to talk a lot about how Lang proposes to solve these problems. I want to move on to some other issues. But it's worth mentioning that Lang's response to this argument is just to bite the bullet. It says, look, mass is an objectively real property, energy is not, and those cases that we thought were cases of conversion between energy and mass are in fact being misdiagnosed in the textbooks. There's a sleight of hand that is occurring, whereby it looks like mass is being converted into energy or vice versa. And I won't go through the details of exactly why he thinks that, but one way to sort of motivate, to sort of provide a very general motivation for that sort of view, is that if you think about what's going on with respect to the electrons and the protons and the neutrons in tritium decay, at no point do the masses of any of those constituent elementary particles change, right? So, you know, at the level of the constituent particles, it looks like there is no actual conversion of mass into energy. Right? So Lang has an elaborate story as to how to diagnose what's going on in these cases. What I want to do is think about this general interpretive constraint that to be an objectively real property, you have to be, it's a necessary condition, you have to be Lorentz invariant. Right? And I want to raise three sorts of explanatory puzzles that arise when you use this sort of constraint. Puzzles that I think can be solved. I think the constraint is a good one, but that point in the direction of how to understand the relationship between energy and mass and special relativity. So the first one I'm going to call cases of genuine conversion. Right? So here I'm talking about things like electron-positron creation and annihilation. So this reaction can go in either direction. Two photons can collide and generate an electron and a positron, or vice versa. And this is a sort of case that, for reasons that I really haven't discussed, Lang's analysis cannot deal with, right? Because this is a reaction where it looks like the change from energy to mass occurs at the level of the individual units or particles or what have you. So Lang's sort of story about how we end up inadvertently shifting perspectives in our physical analysis to generate the conversion of energy into mass just doesn't apply in this particular case. And this is by no means isolated, right? There are a whole bunch of them. I'm not going to talk about them, but any of these, I think, are going to pose problems for the way Lang wants to try to diagnose the relationship, the conversion of energy into mass. And I think it's worth noting that if you look at the electron-positron creation, right, the threshold energy that's required to get this reaction to go is exactly what you would expect if the energy of the photons was being converted into the mass of the electrons, right? The minimum energy of the photons that's needed is exactly the sum of the rest energies of the electrons, right? So here's what we want out of this puzzle. Here's what a solution to this puzzle would look like as I'm setting it up, right? We want an explanation of the changes taking place in these reactions that only appeals to objective physical properties, right? So for example, in the electron-positron creation, it looks like we have the conversion of energy into mass. We want to be able to understand what's going on there, right? The changes that are happening dynamically in the system in a way that only appeals to Lorentz invariant quantities, right? So in particular, not energy, right? So that's what it would take to solve this sort of puzzle. Second puzzle, which I'm going to call explanatory differences. So consider two different particles that are equally massive, that are moving, that have different kinetic energies in a given frame, right? What explains, what are the objective physical facts that ground the difference in those dynamical states, right? The two particles are moving with different kinetic energies, but kinetic energy, according to this criterion, is not an objectively real property, but yet we know that the two particles interact differently dynamically, right? So the question is sort of, what are the objective physical properties that distinguish those two particles, if not their kinetic energies, right? Similarly, if frame-dependent quantities not represent objective physical properties, what physical facts distinguish the dynamical state of a particle before and after the application of a force? So imagine a particle moving along inertially, and you hit it for a specified period of time with a force, and then turn the force off, and it continues to move inertially, right? Velocity isn't an objectively real property, so there is no, so that isn't an objectively real difference between the state of the particle after the application of the force and the state of the particle before the application of the force. But of course, there is some sort of physical difference between those two situations, because a particle that was co-moving with the original particle is now in relative motion after the application of the force, right? And so there is some sort of physical property that has changed, right? But can't be the kinetic energies or the velocities, right? So what we want out of this puzzle is an account of how these particles or states differ, right? That the state of the particle before the application of the force and the state of the particle after the application of the force, or the states of the particles moving with different kinetic energies that only appeals to Lorentz invariant objectively physical properties, right? That's what we want. Okay, third puzzle, composite mass. So a system's mass is partly constituted by the kinetic energy of its components, right? This is an observation that plays a central role in Lang's own analysis of the situation. And you can see that, for example, by just noting that if we consider both of these particles as a single system, right, each of them have a particular relativistic free energy, and so if we consider this as a single system, the mass of that system ends up depending in part on the velocities of the two particles. So in particular, if we then heat this system, speed up the velocities, we get a change in the mass of the system that depends on a change in the velocities and depends on a change in the kinetic energies, right? So when we think about the mass, in special relativistic dynamics, when we think about the mass of a system, it depends on the velocities, the kinetic energies of the components of that system, right? And you can sort of show generally, by doing an approximation, that the mass of a composite system of special relativity is always going to be a sum of the masses of its constituent parts plus a whole bunch of kinetic energy terms, right? And so this gives rise to another sort of puzzle. How do we make sense of this? If mass is an objective physical property, but kinetic energy is not, right? Because in this particular case, it looks like the kinetic energy is partly what determines the mass of the system. So what we want out of this puzzle is an account of system mass that appeals only to the objective physical properties of its constituents. Okay. So we have three puzzles that I think are raised by the idea of a Lorentz invariance as an interpretive constraint, and three different conditions on what it would take to solve those puzzles. Good. Okay. So what I want to suggest is one way we might try to get out, well, one way we might try to solve these problems. And the solution, I think, is to think about the dynamics as unfolding in Minkowski spacetime, not in terms of frames. So here we have the light cone, we have a particle trajectory, and associated with that particle trajectory at each point along it is a four vector that is the four momentum. Right. And the important details about this sort of characterization of special relativity is that the dynamical state of a particle is given entirely by its four momentum. Right? And that the magnitude, at least for a particle, right, the magnitude of the four momentum does not change, only its direction in spacetime changes. Right? Because the magnitude of the four momentum is fixed at a particular value that determines both the mass of the object and its rest energy. In coordinate terms, this is what the four momentum looks like. The only important thing to note here is just that the time dimension, the time component, or the zeroth component of this vector, it's in some sense a measure of the energy. Good. Okay, so how does this help us? One other thing. For an isolated n-particle system, the sum of the four momentums of its components always remains a constant, right? Where that sum is just regular vector addition in Minkowski spacetime. Right? That's an important detail. Right? You want to know the four momentum of an entire system, you just take all the four momentums of its components and you add them together, right? And if the system is isolated, that net vector can't change. Okay, so I think that actually this picture provides us with the tools for understanding how to resolve these sorts of puzzles. So let's start with the explanatory differences puzzle. Right. The thing to notice that I think gets overlooked when we think about this in terms of frames is that the four momentum encodes actually two distinct Lorentz invariant physical properties. It encodes a magnitude and it encodes an orientation in spacetime. Right? That orientation is Lorentz invariant as well. Right? So in particular, as the orientation of a particle's four momentum vector changes, its velocity and kinetic energy change relative to a fixed inertial frame. So these two four vectors, four momentums, have the same magnitude, right? But as they rotate, they are associated with different kinetic energies. And so this identification of four momentum orientation as a distinct and objective physical property actually solves the puzzle of explanatory difference. So consider two different particles that are moving, two different particles of the same mass, right, whose four momentums are of the same magnitude, that in a given frame are moving with different kinetic energies. Well, that corresponds directly to this pair of four momentums. And of course, they have different orientations in spacetime. So if we think of the orientation of an object's four momentum as an objective physical property, then we can explain what the physical facts are that are different for those two particles that are moving, that have the same mass but are moving with different kinetic energies. Namely, they have different orientations. Their four momentums have different orientations in spacetime. Composite mass. So consider again our two-particle system, right? So suppose that the particles are moving away from each other or moving towards each other, right? Again, we have a net four momentum for the system. Because the system is isolated, if the system were isolated, that would remain constant. But as we heat it, right, what happens to these four momentum? Well, they rotate, right? The particles speed up, right? We don't change the mass of the particles, so they have to rotate in a way that preserves their magnitudes. But you can see that when you do that, and then you add up the net four momentum of the system, you end up with something greater than you originally had. And of course, that greater net four momentum is associated with a greater mass of the system. And so we can actually explain how the mass of a composite system in special relativity is a product of objectively real features of its constituents. Namely, it's a product of the magnitudes of the four momenta of their constituents and their orientations. But both of those are objectively real physical properties, right? And so nowhere in this story do we actually have to invoke kinetic energy at all, right? So we can ground the notion of system mass using objectively real properties of the constituents. Okay.
That's 20 minutes.
Okay, so I'm almost done. Okay, so now let's return to this case, the cases of genuine conversion, right? This is a little bit more complicated. So recall what our aim was, right? What we wanted to do with these cases of genuine conversion. We wanted to explain what was going on in these reactions in a way that appealed only to objective physical properties, right? It looked like, in the case of electron-positron creation, it looked like we were converting energy into mass, and what we would like to do, or be able to do, is to tell some sort of story about how the properties are changing in the reaction that gives rise to the mass in a way that only appeals to Lorentz invariant physical properties, right? That is to say, not energy, right? That's what we want to be able to do. Right? Good. So consider the case of the electron-positron pair creation, right? The two green four vectors are the four momenta of the two photons. After the collision, right, we get these of course are four vectors of magnitude 0, because photons have no mass, and these are the output four momenta of the electron and positron. And you'll notice that the four momenta that come out have to be such that, because the system is isolated, the net four momentum vector of the system remains the same. Right? So it's a constraint, it's a conservation constraint on how this reaction proceeds. Right? Now, this is a genuine transformation of objectively real properties, but it's not a transformation between mass and energy. It's the transformation from one set of four momenta, magnitudes and orientations, to another. So the idea is, what's going on? You can think of what's going on in this reaction as the four momenta rotating inward, right? The change in orientation is an objectively real property, right? As are their magnitudes, which have to change as they rotate inward in order to preserve the magnitude of the system's four momenta. So the creation of particle mass is a consequence of the way that changes in the orientations of the component four momenta, constrained by the conditions that the total system's four momentum remain fixed, require changes in the magnitudes of the component four momenta. So the idea here is that mass arises in this reaction in virtue of how the magnitudes of the outputs of the four momenta are constrained as the four momenta of the inputs rotate inward. So, just to sort of drive the point home, you can imagine, so as these four momenta rotate inwards, their magnitudes get larger and larger. The largest you're going to reach, of course, they never go above this horizontal line drawn between the tips of the green arrows, because we have to have a fixed magnitude on the net four momentum of the system. But you can imagine that the case where the most mass is created is the case where these rotate all the way inward, right? So the idea is that you can think of mass as being created in these reactions, not because energy is being converted into mass, but because it's a product of combinations of changes in objectively real properties, right? That just drops out of how the geometry of Minkowski spacetime works. So these are genuine physical changes that I think are misleadingly characterized as the conversion of energy to mass. Energy is not converted into mass. At no point is in this account, in this picture, right, is energy ever invoked. But yet I'm able to explain how, starting from these two and ending at these two, you end up with the creation of mass. Thanks.
Right. The components of the full vector, the first time-like is energy, and the other was a mass. So the change, and those components are not Lorentz invariant. So why do you say something's conserved?
So sorry, which?
The components of a full vector, the time-like component is energy, and the other three are momentum, which is related to the velocity.
Yeah.
Right. So why do you? Those individual components are not Lorentz invariant.
That's right. That's right. But but the magnitude of the vector is.
Right. So, but only the magnitude. But when you change the direction, you change the individual components.
You are changing those components too, but those components are not. I mean, the trick is to sort of to describe what's going on in a way that doesn't appeal to anything that's not Lorentz invariant. It's true that in the course of telling the story of the vectors, rotating inward, as it were, there are frame-dependent quantities that are changing along the way. Right. But we don't want to give an account of what's going on in terms of those quantities.
Yeah. Well, other point is, the original quote, I don't see why you associate reality with Lorentz invariant quantity, which is not observable. You can actually observe length, but I can't directly observe space-time interval for momentum. So why do you equate reality with Lorentz invariant quantity?
So maybe I'm not. So Lang's understanding of relativity, which is also my understanding, is that one of the things that relativity shows us is that, in fact, there is no objective physical fact about the length, say, of a rod. There is a physical fact about its length in a rest frame, right? But because that frame isn't preferred over any other frame, right? We can't say that that is the length.
But you're sort of assuming absolute means real, which is a classical concept of relativity. My understanding of it is that relative is real, and this, for me, the reality of this pen is its length. That is real to me, because I can measure it. So you're sort of denying my ability to measure something, saying that's not real. You're saying only the thing which you calculate is real, which is like hidden variables in quantum mechanics. You're denying observation, and you're saying the thing I calculate on paper is the reality, the hidden thing.
So,
not quite.
So I get the sense that this is perhaps a more extended, discussion than I'm going to be able to give it here.
Yeah.
Let me just say that, I mean, the motivation for that sort of interpretive constraint is that what's going on physically with regard to the dynamics shouldn't depend in any way on the observer and quantities that are frame dependent that an observer ascribes to a system. Right? I mean, that's the basic intuition behind this sort of interpretive constraint. I mean, so that's the motivation.
Probably, yeah.
Yes.
It's a longer discussion.
James.
Do we have time for questions?
2 minutes.
Okay. My question is whether Minkowski space-time is really playing a role, or whether it's just meant to illustrate, and whether it's really just the fact that you're talking about four-dimensional quantities that matters and not Minkowski space-time. And then in relation to that, I just wonder why you didn't mention the mass energy, the four-dimensional mass energy, which is different between the two particles that have the same rest mass, but one of them's moving and one of them isn't in every frame. So is he also would seem to be a candidate for the difference that explains why they're different?
So I want to ask you about that last part afterwards. I'm not sure I know exactly which quantity you're referring to.
Okay.
I am thinking in the context of offering this sort of a diagnosis of what's going on. I am thinking of Minkowski space-time as, you know, some real thing that's playing a dynamical role, right? I know that that view isn't, you know, plenty of people here in the audience aren't sympathetic to that sort of view. Yeah. And you might be able to tell a story, a comparable story, but at least for me, with respect to trying to come up with some preliminary analysis of what's going on, I took it as sort of a real construct, physical construct.
Okay. Well, that really is about out of time since you're a whole half an hour, 20 minutes ahead. Let's say thank you.